My name is Yousra Hafidi. I'm a postdoc researcher at the Eindhoven University of Technology, and today I will be presenting my research work entitled Fair Mutual Exclusion for N processes. This work has been done by me, Jeroen Keren, and Jan-Fries Ograute. So let me first start my presentation with this slide in which I introduce mutual exclusion problem. So we are in a system where there are two processes, process 0 and process 1, and they both are using a shared resource, which is called a critical section. So in which just one process should use it at a time. So many algorithms appear in order to deal with that problem. First, the classical algorithm, the famous one proposed by Peterson, original algorithm has been proposed for two processes. And then other versions appear to generalize this algorithm to consider more than two processes. For example, we have the version that uses filter lock structure, and also the version that uses a tournamentary structure. So in this talk, we will focus on the tournamentary version. Okay, so first I will explain the concept of Peterson's algorithm for two processes, so the classical one. In order to synchronize the access to the critical section, Peterson's algorithm uses two shared variables. We have flag variable, and this variable indicates if a process requests access to the critical section. And the other variable indicates that a process is waiting for the other one. So suppose that we have process 0 that wants to access to its critical section. It first sets its flag, so flag of process 0 is set to true, to say to the other process that I want to access to the critical section. And also it sets a wait variable to 0 to indicate that although I want to get access to the critical section, but I'm waiting for process 1. And then it enters to a waiting loop in which, as you see here, there is a while loop and there are two conditions. So either the flag of the other process is true, should be true, and also the wait variable should be assigned to the current process. So as you see here, it can only get out of this waiting loop if either the flag of the other process is false or the wait variable is assigned to the other process. So once it gets out from this waiting loop, it can get access to the critical section. And when it gets out, it resets its flag to false again in order to say that I'm finished with the critical section. So the same code is for process 1 as well. Now we have the algorithm. In order to say that the algorithm is correct, we should verify some requirements. And the most important requirements are, of course, mutual exclusion. The main requirement says that only one process should be in the critical section. And also we have starvation freedom, which is a liveness property. It says that once a process requests access to its critical section, it will get access in a finite number of steps. So it will not wait forever. And we have another important property, which is bounded overtaking. It means that there is a bound that we can compute on the number of rounds that a process will wait in order to get its turn to access to the critical section. So these three requirements are verified in the literature. And I would like to take your attention to the B, which is the bound for the version of two processes is 2. It means that a process that requests access to the critical section, it waits for a maximum of 2 rounds before it gets its turn. Now I will explain the generalized version for more than two processes. And of course, we focus on tournamentary version. In order to explain that, I will first explain what is this tournamentary structure. A tournamentary structure is a binary tree of at least one level. So here we have a tree of two levels. So it depends on the number of processes. And the processes are actually candidates and they are attached to the leaves. And each two processes are competing together in a node. So we have a process at the left, and we say that its side is 0, and the process at the right, so the side is 1. And the winner in each node moves further to the parent node, and the winner in the root node is the winner of the tournament tree, and it is privileged access to the critical section. So as you see here, we need functions in order to compute the initial position of processes in the tournament tree, and also a function or a formula in order to compute the parent node. So all of these are defined, and they will be used in the algorithm. Also for this version, for this generalized version, we have shared variables between processes. We have flag, but this time we have two flags for each node. So we have a flag for the left process and a flag for the right one. And we also have a weight variable for each node, which can be at the left side or the right side in order to indicate which process is weighted. So now, in order to verify this algorithm, we need a formal model. So we need to specify this algorithm, and we do it using MCRL2 language, which is a process algebra with data associated with a toolset for modeling and simulation and verification of concurrent systems and protocols. So let's start specifying our algorithm. Now, first, we would like to say that we have specified the enter and leave of the algorithm explicitly using actions, and this is for verification purpose. And also, the first thing actually is also how to deal with the shared variables, flag and weight, how to specify them. So for flag, for example, we introduce a process equation that specifies reading and writing these variables, and we specify the process, we specify the communication between this variable and the process instance, and the same thing for weight variables. So for the algorithm, it is straightforward to specify the process equation of Petersons algorithm. So first we set the flag, and then we set the weight variable, and then we enter to a weighted loop in which we get out of it only if the flag of the other process is false, or the weight variable is assigned to the other process. Once we get out of this weighted loop, we enter to the critical section. So if we are in the road, of course, and then we enter to the critical section and leave. And then if we are in a node that so if we are in the road, we enter to the critical section and leave. Otherwise, we move further in the tournament tree to the parent node. So we execute Peterson's algorithm again for the in the parent node. So once we finish, we reset again the flag into false. Actually, so we have the specification of this algorithm, and now we want to verify some properties. So we use mu calculus to specify properties. Mu calculus is the first order model. The first order model mu calculus is a temporal logic that extends Hennessy-Milner logic, with fixed points and data. So this is a mutual exclusion property that says that at any time, at most, one process can be in the critical section. And this is formalized by saying that invariantly there are no two consecutive enters without an intermediate leaf. So we cannot find in the state space two enters without an intermediate leaf action. This property is verified, so using MCRL 2 set, so it is true. And we have another property, which is the liveness property, starvation freedom. So if a process requests access to its critical section, then it will be able to have it in a finite number of steps. And this property also called lockout, eventual access or finite steps. And it is the strongest liveness property of Peterson's algorithm, as I've said. The formula says that if process requests access to the critical section, it is allowed to enter within a finite number of steps. So the least fixed point in the formula ensures that after requesting the critical section, actions other than enter can only be taken a finite number of times before enter is taken. And this formula this property is proven false. And the counterexample is given by MCRL 2 set is the following, in which we see that process 0 requests access to its critical section. Also, process 1 requests access, but we have a cycle here in which only process 2 that requests access get, so enter, leave, and then request again and enter, leave an infinite number of times. So process 0 and 1 will never get their chance. In order to execute that counterexample, so let's suppose we have this tournament tree, so processes 0, 1, 2 are attached to their initial positions, and the flag variables are all set to false, and the weight variables are set to the left processes. So process 0 requests access to its critical section, then it sets its flag to true and the weight to 0, and then process 1 that also sets its flag to true and the weight to 1, so it requests also, and then process 2 comes and also requests, then it twins the competition here in node 2 because there is no other candidate in the right side. So it wins the competition and moves to the root. And also it wins the competition in the root because there is no other competent in the left side. And it gets access to its critical section. Then it sets its flags to false again. And it does the same thing again and again. And as you see, process 0 and 1, for example, process 1 can execute something, and also process 0 can execute something, but they do not. And the only one that progresses in the tree is process 2. So for the version of 2 processes, this property is verified, and the version of 2 processes is executed in every node. So for processes that are attached to a same node, this problem will not appear. But yeah, in this case, we can say that Peterson's algorithm preserves the individual progress of processes that are attached to a same node. But the issue is that how to consider the individual progress of processes that are not attached to a same node. So for the counter example, for example, we had the problem with process 2 that is getting access every time, and process 0 and 1 are waiting forever for their turn. They won't get it. So how to consider the individual progress or of processes that are attached to node 1 and process that is attached to process 2. So we got expired from the counterexample, and we proposed a new variation of this algorithm in which we propose a fair mutual exclusion algorithm for more than n processes in order to satisfy this property. So the first thing that we have done is specifying this next variable. And this next variable help us to introduce the information about the other side of about the other processes that are not attached to a same node. So process 2 should know that process 0 and 1 also request access to their critical section, and it should at some point its progress should be bounded out at some point in order to give turn to the others to get their turn. So we specify the next turn variable function, and we block the progress of, for example, process 2 until process 0 and 1 get their turns, and we know this from their flags if they are false. So the main modification that we've done in the algorithm is adding this waiting loop here, and including the parameter, which is the information about the next turn. So basically, process 2 here, when it comes to this waiting loop, it will wait until process 1 and 2 get their turn. And then it can request again an access. So we verified the same properties for this version also to be sure that the algorithm that we proposed is correct. We verified mutual exclusion, and also in this version, starvation freedom is satisfied. So now we have another interesting property that we can verify, which is bounded overtaken. So the formula is the following. So the formula says that for every process I, if it requests access to the critical section, every entry, every enter action other than enter of the current process increments the parameter n, and if n of the grid is fixed point, and if condition n is violated, means that this condition, if the n is if the b is bigger than n, then the property is false. And then we find that this property is also verified, and the bound for 3 processes is 4. We also verified for 3, 4, and 5 processes, and this is the result of our experiment. And we use a timeout of 4 hours, but since the algorithm is really complex, we run into state explosion problem, of course. Like you can here see the time how it explodes, and for 5 processes it is more than 4 hours. So we asked the question how to compute the bound for more than 5 processes. And in this case, we had to give a proof, a formal proof that proves that the bound, there is a bound for any number of processes, and the bound that we found is this one. And by this, we have proven the correctness of the new variation of the algorithm. So to conclude, I would like to remind what we have done in this research work. So we have specified Peterson's algorithm for more than 2 processes, of course, Tournamentary version using MCRL2 language. We verified properties and explained why starvation freedom is violated in this algorithm. And also we suggest a new variation to consider the previous problem. So also we specified this new variation and verified it using MCRL2. And we defined, since we ran into state explosion problem, we defined a function that computes the bound and given a formal proof to prove its correctness. Maybe there are some open questions. The first one is how to reduce maybe we can propose other versions that reduce the maximal waiting period, this bound. And also another open question is that Peterson's algorithm, it is known that it sometimes, or now in modern architectures, it fails. But an open question is how to implement it or how to resolve this problem in these modern architectures. And this brings me to the end of my presentation, and I'll be happy taking all the questions that you may have.